Video cameras used to look like this. They were massive devices weighing several hundred pounds, and they cost thousands of dollars. Now, cameras look like this, or this, or this. They've become tiny, cheap, consume little power, and produce pictures of truly amazing quality, and that's why you see them everywhere. And nowhere more than in automobiles. Just a few years ago, backup cameras were something you'd see only on certain high-profile vehicles like minivans or SUVs. Now, just about everything on the road has one, or two, or more. In fact, as driver assistance systems have become more common, cameras have begun to really proliferate. Think about it. You might have not just one camera to show if there are objects below your rear view mirror's field of view when you're backing up, but cameras on all sides of the car for full 360-degree coverage. You'd likely have some kind of sensor, either image or radar, in the front for adaptive cruise control and preemptive braking. Perhaps there's a separate camera that's focused toward the edge of the road to sense road signs and speed limits. And cameras to replace the side mirrors. Maybe a separate camera pointed toward the front that continuously records video just in case of an accident. And don't forget inward-facing cameras that can check for drowsy drivers and proper use of lap and shoulder belts. That's a lot of cameras. And don't forget, those cameras are increasingly high-resolution devices streaming high-definition video to an electronics control module that needs reliable, uncompressed video for its machine learning functions to work. So, how do you reliably move that volume of data in a harsh environment like an automobile? Well, let's think about it. Modern cameras are most frequently based on a CMOS image sensor. Each photoreceptor element, and a single image sensor chip contains millions of them, is associated with a color filter, red, blue, or green. The image sensor measures the intensity of light falling on each photoreceptor site, converts the measurements into digital values, and then continuously sends a stream of converted values off-chip, either via a parallel interface or over a set of serial data lanes. In addition to the video data, the sensor has to send synchronization information to indicate when it's at the top of the frame and when it's at the beginning of a scan line. And most sensors contain dummy pixels along the border, so it may have an output to tell the world when it's transmitting active video. And what about the display? It may have a parallel interface as well, but frequently the display may have a more standard interface technology like HDMI or DisplayPort, and most often the camera doesn't directly drive the display anyway. Both the camera and the display connect to an electronics control module that might add annotations to the display, or combine the images from multiple cameras onto a single display unit. And just think about the sheer volume of data. A full HD image consists of 1,080 rows by 1,920 columns. That's just over 2 million pixels, and each pixel consists of a red element, a green element, and a blue element. Now we're over 6 million data elements to send, and let's say we're sending 8 bits per data element. That means we're sending nearly 50 megabits for every frame. Now multiply that by 60 frames per second, add blanking and overhead, and you get the bad news. Your data rate for just one camera is over 3.5 gigabits per second. So much data, so many interfaces. How do you manage it all? Well, Maxim has the answer. GMSL, or Gigabit Multimedia Serial Link to you. GMSL is used in Maxim serializers and deserializers, and they greatly simplify the design and implementation of video systems in harsh environments like automotive applications. Here's how it works. Instead of connecting the camera directly to the system on chip in the ECM, the camera connects to a serializer. The serializer takes the pixel data and the sync pulses, converts them to a serial bit stream, and transmits the bit stream over a coax or a shielded twisted pair. At the other end of the cable, a deserializer decodes the serial bit stream and delivers the recovered video and sync data to the ECM. It does all that at over 3.5 gigabits per second. That's a neat trick. But to make it work, you have to think like an engineer, because there are a lot of engineering challenges to overcome to make even the most robust system work at gigabit speeds. Let's break down a few of them. First, the cable itself. Sending a gigabit data stream down several meters of coax, or twisted pair, requires a lot of planning. There's signal loss, coding, bit error rates, and signal conditioning to think about. And then there's control. If you're the ECM, how do you control the cameras? You really don't want a separate wire just for that. It would be nice to be able to control the camera over the same cable that's carrying the video. And it would be nice to get audio and status indications across that wire as well. And, of course, there's the interfaces. Different cameras have different interface requirements, and the same is true of displays. The serializer and deserializer need to come with a selection of interface types so that most camera and display devices will be covered. And finally, while we're sending billions of bits per second, we still have to be a good citizen. Sending data that fast just screams electromagnetic interference. We have to take active measures to reduce emissions. Oh, and did we mention that the automotive environment was quite hostile to electronics? We need to plan for ways to detect faults in the cable that connects the serializer to the deserializer.